I would like to say hello for everyone, and thank you for attending my presentation today. As you mentioned, the research work that I'm going to present that is about enhanced construction progress monitoring, and me as a PhD student here have worked there with this topic under supervision of our supervisor, Dr. Shen, and the co-supervisor of Dr. Barati here at University of New South Wales. So we know that the progress monitoring in construction industry is not only important for measuring the progress of work, but also it is important for decision making and also for improving productivity in construction industry. Currently, we can say that the traditional progress monitoring is used in the industry, and that is, we say it has some problem that's time consuming, and we can say it's error prone and biased. And due to these kind of problems, the result for the construction project is usually that the construction project will be delayed, and sometimes there will be cost overrun, and also there might be disputes among clients and contractors. So with these problems, the research community has started to use different reality capture techniques, for example, image-based or photogrammetry method or laser scanning, TLS, and GPS, RFID, and EUWB. Among these, the first two will be used for data collection for case-in-place activities, and others will be used for tracking resources. And in addition to that one, the methods that research communities they have used for showing the progress through these new methods that they collect in the data. For example, they have used like color codes to show the activity progress, whether they're ahead or behind of the schedule. In some researches, they have used the percentage, but that percentage is also as per the number of objects detected in the scan data from construction site. And in some other researches, they have used different other methods, like showing some elements either ahead of schedule or some elements behind of schedule as a list. For example, let's say like column ahead of schedule or behind. So in total, if you look back to the traditional methods in the previous research works, there are some gaps that we need to be scrutinized and to do some research works. For example, the static data collection tools they have used in the previous methods, data collections with these static tools needs to be collected from several positions to cover the entire site. And also sometimes these tools will be under influence of environmental factors. In addition to that one, it's very important in terms of our from progress monitoring perspective, that is to need to have a detailed progress analysis of the work. So based on these issues, we have provided our objectives of the work, use a mobile scanner instead of the static ones, and also to filter out the noise and get object of interest from the scan data effectively, and to measure the progress of work accurately in terms of percentages. Based on those objectives, we provided our research methodology in 3 steps or 3 stages. The first stage, which is digital twins, we have as designed BIM model on the one hand, and on the other hand, we have the acquired scan data from construction site. In this phase, we are going to filter out the noise and redundant element from construction site, and we will have a clean point cloud, and we will convert back that point cloud to a BIM model. On the second stage, we are going to indicate the progress of work in 2 stages. First, we are going to apply the color codes for those activities, and later on, we are going to take the volumes of the material, and as per that volumes, you are going to calculate the progress percentages. And third stage, that progress percentage will be used for updating the schedule, which is not covered in this research, and we're going to focus later on. As we mentioned, the filter of the noise and redundant element, The forecast of the filtration here is based on the benchmarking point cloud. We generate this benchmarking point cloud from as designed BEAM model. That is a virtual point cloud, and that is a clean point cloud without any noises, and that include only those objects which we want to take it from scan data. And we apply a mathematical method Hausdorff distance to that one when we register these 2 point clouds, and we clean or filter out the noise and redundant elements that we don't want. So to apply the result or this methodology to to show the validation of this methodology, we conducted a case study here at engineering building of University of New South Wales. The case study has 2 rooms, a meeting and a kitchen. We accept all the furnitures and the kitchen staff as noises, and the collected data was collected with Xuesong Z-Provo scanner, as you see in the left corner. And we also provided a BEAM model for that 2 rooms, as you see in the middle. And also we generated the benchmark point cloud from this BEAM model only for walls, as you see on the right with red color. So that benchmarking point cloud includes only walls because the focus of the case study was only the walls for this study. So we also cut the point cloud that we had from the side with 2 horizontal plane to show further progress of the work since we focus on the walls. These horizontal planes of which we have the 2 sections of them. In total, the case study will have like 4 cases. The case 1 with 0 progress, case 2 also partially completed, and case 3 is also partially completed, and case 4 is the complete point cloud that we have from the side. Once we have those point clouds, then we are going to register these point clouds and filter the noise and convert back to a BEAM model. These steps will cover these 5 steps. First, we create a benchmarking point cloud for the elements that we want. Then we register these 2 point clouds. We apply Hausdorff distance. Later on, we apply an ISARC algorithm, and finally we convert back that to a BEAM model. The result of those 5 steps has shown here clearly in these figures. Part A shows the registration of both point clouds, the benchmarking point clouds and the point clouds from the site. And part B shows the result of Hausdorff distance, which only covered the walls, and we removed all the redundant elements like columns and others, and also the other noises that we accepted, the furniture and others as noises. Still, there were some additional points as noises, and we applied ISARC algorithm. Those points covered with different planes, and we removed them. And the part B shows the clean point cloud only for the walls, which was object of a case study. The same procedure was accepted for 2 other cases, which was shown in E and F, because the focus was to progressively show the progress of the work for the walls. Then we convert these point clouds to BEAM model, as you see G and G, H and I, like progressively the work progressed, and until that we have a complete BEAM model. Here, if you see the BEAM model on the left side, we removed intentionally 2 walls. That is because to show or simulate the ahead or behind of the schedule activities, which we will show it later on. The second phase of this case study was showing the progress analysis, and we compared the as-built model to the as-planned model, and we applied the color codes whether they are ahead of schedule or behind. Here, as you see, the red color shows those activities which are behind of the schedule. The blue activities are on schedule, and those with no color, or say white color, those are ahead of the schedule. And for Understanding the progress in terms of percentage, we used Python and Dynamo. We have the volume of these elements, and we compared the volumes and we calculated the progress percentage for all these walls. As you see here, we have the activity for the walls, and also we have the activity description. Then we have the as planned data, that's the volume for all these elements. We have the volumes for the as built beam models, and we compare as per these two and we calculate the progress percentage. The progress percentage, as you see, have the last column in case 4. They are not exactly the 100%. They are somehow more than 100 in some cases, in some cases less than 100. So that's why it needs to calculate the error in each cases. So for that case, we wanted to calculate the error in each case, and that error was easily calculated for each case, and then we calculated the absolute value for the errors in each case, and finally we calculated the average absolute value till to reach to calculate the total accuracy, which is around 95.9%. Here I should mention we didn't cover the accuracy of the some like the tools, so that was only for the progress percentage. In total, if you saw the conclusion of this work, we used the SLAM-based mobile scanner. It's a new instead of the static one. We extracted object of interest, which were walls, through using Hausdorff extents. And also we calculated the progress of work based on the material volume, which later on that will help us in procurement management and also allocating the resources. And there will be some like other research works limitation that is not applying the color code to the head of the schedule activity, which will work on that one in our future works. So as I mentioned before, this research was done in University of New South Wales. There we have a laboratory, Autonomy, Intelligence and Construction Laboratory, ICON. And we are around like a group of PhD students, around 8 students working in that area. So with this one, I finish my presentation here. If there is any question, I will be more than happy to hear that one and to discuss.